Welcome back and continuing our discussion of enolates in chapter 19. We're going to look at how enamines are enolate equivalents. Enamines we learned how to make in chapter 16 by reacting secondary amines with aldehydes or ketones. And after we've done that, we can react the enamine itself with a aldehyde or a ketone, in this case aldehyde, and do an aldol reaction. Remember, it's what gets attacked that indicates whether it's an aldol or a Claisen. Here's a different enamine. Here it's attacking an ester. That's a Claisen condensation when an ester gets attacked. Mechanism is pretty close to the mechanism of the normal aldol mechanism, where we use the alpha position of a ketone or an aldehyde or an ester. Here we've got the enamine with its pushy lone pair acting like a nucleophile on the position that's called alpha, generating an iminium ion. And what happens in the next step is twofold. We protonate the O minus, that would happen first. That's why that's in black. And then because we also have excess sulfuric acid and lots of water, we're also going to do the hydrolysis of the iminium species that we generated here. This is an iminium. Water attacks, and you get an oxonium, which gets neutralized. We're also going to protonate this to make it a better leaving group, which probably happens first. And then we're doing an elimination of the ammonium ion right here. So review this mechanism on your own. It's probably going to be on the test, and I think you're capable of doing that on your own now. Similarly, if we did a Claisen condensation, we're starting over here. It's attacking an ester. That's why it's a Claisen. So notice the enamines, the attacker here and here. When it's an ester, there's also a leaving group. When it was an aldehyde, there's no leaving group, so it's just acid-base after that. Here, the leaving group gets kicked off. And you don't have to worry about a base taking the H from the position that's alpha to both because you never had a base around. Ah, that's good news. So you go straight off with hydrolysis. There's water attacking the iminium just like it did here. Don't have to protonate your O minus because you didn't have one. This looks pretty much the same as up here. Acid base to deprotonate your oxonium. Protonate the amine to make it a better leaving group. And then elimination. Base grabs H, sigma becomes pi, leaving group protonates, so it's a better leaving group and leaves. And we have the result here. That's a beta keto ketone here. And that's a Claisen result. And here's a beta hydroxy ketone. That's an aldol result. So let's see if we can put this to use. We're taking 3-hexanol. Going to react it with PCC first. 3-hexanol with PCC first. That's going to generate a ketone. That's what PCC does to secondary alcohols. And then with diethylamine, in the presence of a Dean-Stark trap, that's for condensation reactions, if you remember correctly. And I just noticed a problem here. Made this on the fly, on the break. And it looks like we're going to get 2 different enamines, and I didn't really want that. I'm going to do a quick little edit here. No, it won't let me. Look at that. That's not very nice. Yes, I can. I'm going to go 3-pentanol. I suspect it's going to be green for some reason. No. 3-pentanols reacted first. There we go. So some weird stuff's happening here, people. Hope we don't have a crash. There we go. So we're starting with 3-pentanol, ending with a symmetrical ketone. I don't have to worry about 2 different enamines. And I won't make you worry about 2 different enamines on the test. That's why I made this correction. And we have the 6 carbons, or 5 now, 5. And we have 2 ethyls, and you pick a direction for your enamine. Right there. And then I'm going to react product 1, which is this thing, with cyclohexanone, followed by excess sulfuric acid. Nice. Typo. Sulfuric. You saw it. Cyclohexanone looks like this. So we're going to attack the carbonyl. Attack the carbonyl. Generate an O-, which becomes OH. And then that's the aldol reaction product. And it doesn't say anything about heat. So we're not going to get a condensation product here. And what's that going to look like? Well, your intermediate I will give you, which will help you figure out the final product. Nitrogen resonated in, and the purple carbons are here. New bond is here to a cyclohexyl species that has an OH here. Don't forget that's a positive nitrogen. And that takes everything up to the hydrolysis step. And hydrolysis cuts this open right here. Let's do it in an unobtrusive color. And that's going to give this result right here. Your original ketone before you made your enamine is back. But it's got new stuff on it. New exciting stuff. Got a new bond right here. And I'll just remind you, if you treated that with not just sulfuric acid and water, but sulfuric acid, water, and heat, that's a triangle, doing my best, then you would get the aldol condensation product, wouldn't you? There's a double bond. And this is a aldol condensation product. A RP for aldol reaction product, a CP for aldol condensation product. And this was part 1. And part 2, same enamine is going to react with ethyl hexanoate. Ethyl hexanoate. And I'll just go straight to the final result, which is a Claisen result this time after the hydrolysis, etc. And I'll write down then hydrolysis. And you'll get your ketone back once again. The ketone you use to make your enamine. It'll have a new bond once again. This time it'll be to the hexanoate portion of ethyl hexanoate. 1, 2, 3, 4, 5, 6. Claisen. I would have to call this a directed Claisen. Enamine style. And that's useful stuff. That's what that is. And before we come back to a big finish with conjugate addition, which I'm doing a little out of sequence, I am going to talk to you about the malonic ester synthesis and the acetoacetic ester synthesis. And this statement from the book is a correct statement right here. Your retrosynthetic analysis on test 2 will require you to use a malonic ester or an acetoacetic ester synthesis. More on that in a second. So these things at the end are potential target molecules. And why I have acetic acid circled is that if your target molecule has acetic acid as part of it, or even a derivative of acetic acid, like maybe an ester of it or an amide of it, then the malonic ester synthesis is the approach you should use. Now, if your target molecule does not have acetic acid as part of its structure, but acetone, then you should use the acetoacetic ester synthesis. Acetone with 2 new R groups, and the synthesis puts those R groups on. So let's run through both syntheses because they're very similar. The top of the screen is the setup. How do you make a malonic ester? Well, you do an esterification reaction of malonic acid. Oh my. Why did I say oh my? Oxalic acid has 2 carbons, malonic acid has 3, and it's a dicarboxylic acid. We have to know that for our test anyway. So there is diethyl malonate. Esters of that have a very special hydrogen, alpha to 2 carbonyls, similar to this here. pKa equals 10 for both. That makes it very easily removed. Here I just made a diazomethane esterification. I could have done a Fischer esterification from acetoacetic acid. That is a name you have not seen before. Does it make sense? I have acetic acid right here and an acetyl group attached, but they don't call it acetyl. They call it aceto. They could have called it acetylacetic acid. It would have made life a little easier. It would sound more like acetyl salicylic acid, where there's an acetyl there as well. So we have acetoacetic ester. The synthesis parts are identical. You can use a normal strong base, nothing special about hydroxide. We use it every week in the lab almost. And it will quantitatively take this H off because the pK is 10. You're generating a C minus. That goes to C minus, which does a backside attack on methyl bromide. And there's your carbon-carbon bond to a methyl group. And similarly, generate a second C minus. Why this position? Because that still has a pKa of 10. And hit it with a benzyl group that has a leaving group. You get a benzyl. And then what's going on here is a whole bunch of review. And this is the nice part about the synthesis. It incorporates a lot of everything that's in test 2. Saponification, we studied with esters. It's going to generate a carboxylate. Saponification using NaOH and water. This will become a carboxylate, and so will this. HCl will protonate both carboxylates and make carboxylic acids. And then beta decarboxylation occurs. If we have carboxylic acid beta to another carbonyl, then we will decarboxylate it. You want to look at that in the previous chapters. Beta decarboxylation. And that will get rid of one of the carboxylic acids, leaving us just with the one version of acetic acid. And notice acetic acid has the two new groups we put on here and here. Methyl down here and benzyl here. And similarly, the acetoacetic ester synthesis has the same type of alpha H, low pKa, easily accessible. Generate a C-, attack an ethyl with a leaving group, get an ethyl. Remove the second alpha H, attack an allyl group with a leaving group, you get a new allyl group. Saponification, acidification, decarboxylation, sounds kind of nice, like a rap song. We'll get rid of the carboxylic portion here, just like it got rid of one of the carboxylic portions here. And you're left with an acetone that has two new groups on it. So get ready for your synthesis, retrosynthesis on your test to be one of these two approaches. Look over all the old practice exams. You'll see, I hope, that the malonic ester is used much more frequently because in your instructor's mind, a product that is a carboxylic acid derivative seems more fitting for test 2 than that which is a ketone derivative. That was chapter 16. So I'm going to stick with that tradition, I think, and you'll probably be focusing on a malonic ester synthesis. Just a little heads up. And we're going to have a long final fragment, and it's an important segment, and it's about conjugate addition. And we will be ready for it on the other side of the break.
Dr. Whitaker?
Toodaloo.